All right. So my name is Samantha Shepard, and we
Oh,
have.
it says we're still off air, according to
Oh,
my phone.
mine says
Oh, it
live.
does? Okay. Okay,
Yeah.
go for it.
So we have. This is part one. Actually, question two. I know my YouTube
Oh.
video says question one, but it's question two, and it says, "How is radiometric dating like an hourglass, and how is it different? And then why are so many different isotopes used?" So radiometric dating is kind of like an hourglass because when you flip an hourglass over, all the sand falls to the bottom. Radiometric atoms are like the individual grains of sand, um, and radioactive decays are like the falling grains from the top to the bottom. You can't predict when one particular grain of sand will fall, but after you do it a couple times, you can tell how long it will take for the sand to fall. So once all the sand falls, you can no longer judge time unless you turn it over again. It's the same thing with radioactive atoms. Once the elements are gone, the rock will no longer keep time unless it receives more radioactive atoms. But just like an hourglass, the rock is also sealed against additional radioactivity, so the likelihood of it gaining more radioactive atoms isn't likely. It's not like the hourglass because the hourglass, the sand falls at a constant rate um, until the end, but with radiometric dating, the number the number that decays in radioactive molecules decreases as there are few atoms to decay. So you get an exponential um, decay, or is it also logarithmic, the one that goes down? I don't know if that's correct, but it's
Mm-hmm.
exponential, not constant, not linear. And then also, unlike the hourglass, there's no way to change the rate at which radioactive atoms decay in rocks. So, like with an hourglass, if you jiggle it or tap it, the sand will fall quicker. It doesn't work like that with radioactive decay because you can add more heat, you can do anything, and it will decay at the same rate. So,
Mm-hmm.
yes.
Awesome. Should I go on to the second part?
Yeah, go ahead and talk about the different isotopes. Why are so many different
Yeah.
isotopes?
Yeah. Okay, so my name is Jessica, and I have the why are so many different isotopes used portion of question two. And we just talked about how each different isotope has a separate half-life. And so um, the more isotopes we have, the more ability we have to date things. That sounds really bad. Yeah, so like if a isotope has a shorter half-life, we wouldn't be able to date it like older things, right?
Right.
And then, but if it had a longer half-life, we'd be able to date older things. So having a variety and having so many different isotopes allows us to date tons of different things. So yeah,
Awesome.
that's it.